I didn't get that right.
It was easy. So
It was the sample of means, right?
Hello and welcome back to Statistics1. This is our last class. It's the final, and yes, that's it. You made it. Congratulations. You made it to the final exam review. Now,
Physically. That's about it.
physically, what is on the test? Problems from statistics, right? We are going to focus on all 9 chapters we covered. However, some chapters are more equal than others, right? To use the correct social justice terms today. So we have bulk of the stuff in chapters 3, 4, 5. Well, 5, 3, 4, 8, and 9 in some sense, but then also 5, 6, 7 will be featured as well. So finally, it's cumulative, has everything that we have covered in the class, and the best way to study for it obviously would be to take a look at all 3 exams and make sure you can do all of your homework exercises. Make sure you complete your homework exercises in my MATLAB, so that will give you practice and also a higher grade as you go along. So some of the concepts that are very important are, for instance, z value and how to transform the x value and the z value looking at the chart. So when we have the distribution, we said that, you know, in the middle, if this is x-axis, in the middle you will have the population mean. But at the same time, you can have another scale, right, which is one more axis. Now this axis is a z-axis, and in that case it's a 0 there. So we have standard deviations to the left and to the right. So 1, 2, 3, 1, 2, 3, and these guys on the red scale are all standardized, right? So we have numbers from -3 to +3, and mu is equal to 0. So z-scale measures how far you are from the mean in terms of standard deviations. And we have the formula, which you absolutely must know, that the z-score is equal to x minus mu divided by sigma. It computes, right, x minus mu divided by sigma, it computes the z-score. And you see that this z-score formula depends on your, so z-score formula over there depends on population mean and population standard deviation. Now we worked hard throughout the course to move away from this dependency of population mean and population standard deviation. We wanted to go and just use the sample. So you must know all of the formulas that pertain to population and the sample. But again, as I said, the idea of the course is to actually deal with the sample. So as you gone through the course, I know that at one point or maybe 2 points, I asked you to start creating a formula bank, right, where you would compare the letters that are used for population and the letters that are used for sample, and then looking at how the formulas are different between the 2 worlds. So if you have the size, whether it's the sample size or the population size, you have capital N for population and the lowercase n for sample. So that was what we were using before. Then you have the mean, and we use the mu and x bar. And then standard deviation, we used sigma for population and s. And through this, I'll just put standard we had the z-scores associated with the population and the t-scores associated with the sample. So these are just the variables that we are using in this course. And then when you are calculating mu, you take the sum of all x values and you divide by how many they are. And for the x bar, you do the same thing. You sum all of the x values of how many they are and divide by the sample. But then for sigma, right, it was the square root of summation of x minus mu divided by capital N, where for s we had to use n minus 1. So summation x minus x bar divided by n minus 1. And at the end, we had our test statistic z to be given as x minus mu 0 divided by standard deviation, which was divided by square root of n. And we had the t statistic that was x minus x bar divided by s divided by square root of n. So these are the test statistic ones. And we also had, finally, the confidence formulas, where we had the confidence level gave us the interval for confidence of interval confidence, and that one was x minus z alpha over 2 times sigma over square root of n, and I should be using capital N over here for population side. There we go, comma, this is x bar, and then x bar plus z alpha over 2 sigma over square root of n. So that was the confidence interval when sigma is known, but now when sigma is unknown, we have x bar minus t alpha over 2, right? It's a t-score now, and it's s divided by n, root n. And then x bar plus t alpha over 2, s over root n. So these are all the formulas that you have now. This part over here is called their error. So in one of your exams, you had to, one of the questions you had to compute the error, which means you don't put any of the other things. It was just that error. Yes?
Oh, for the standard deviations, aren't they like squared x minus?
Oh yes, they are squared. Oh my. They are squared. Yes, yes, yes. Good. Standard deviations are squared. So these are the things, and if I ask about the error, like there was a question on the exam, you should just be computing, this part to get your error. So the error question on a previous exam was 0.6. There were some decimals to it, but 0.6 was what we had. So that's what we have for, and pretty much the other formulas that you pay attention to are all in probability, right? In chapter 4, I believe. So, everything else other than chapter 4 falls into these. We did have the sample, like the one problem that was a gift, and pretty much all of you didn't do, is that mu x bar is the same as mu, so you just have to control C and control V into that position, and then that the sigma x bar is equal to the sigma divided by square root of n.
Wait, so what did you mean by notation? Because you subtracted 2 and then you wrote notation.
That means that the notation was terribly wrong. I'm not sure what it is for some problem, but notation means use the proper mathematical terminology. Writing. Yes?
Yeah, no, I just wrote
Oh.
mu x equals mu.
Mu x.
Yeah, I didn't write x bar.
Oh, x bar.
Yeah, I didn't.
No, there was something else there probably. All right. So what else do you have?
So the confidence interval when it's unknown, that's the t-score.
Yes, because you don't have the standard deviation for the population, but you can find one for sample. So we use that one instead.
I'll bring it up after.
So we're going to
Yes.
Could you just go a little bit more in depth on the Z, the formula of the Z and T?
These are the test statistics. Test statistics, that was chapter 9. Well, they are in chapters 8 and 9, but we use them in 9 to test. What you do is you use it to do the rejection or non-rejection of arguments for hypothesis testing. That's what it is. Yes. Yes.
Can you give us 2 examples? Can we go through 2 examples where it is sigma, using that formula, sigma is known versus unknown? I mean, what that would look like? Because
well, it's in wording, and this is something that you guys have to be very careful with statistics class, and the way you read, you have to be really focused. You look, if there is a problem, okay, so let's say there is a problem which states, it's chapter 9, hypothesis testing and all of that stuff, but the problem says like this. Shoe size of college students the average shoe size. The average shoe size of college students is known to be, let's say, an 8.3. Well, and now here's the next sentence, which is what determines which way it goes. The next sentence says, the sample we observe is given below. Now, what is that? It's going to be a distribution, right? It's going to be data for what these guys did. So you have some data over here. Observe that at no point, right? So find, do the hypothesis testing. So this is not a concrete example. This is more of the conceptual example. So see, I never wrote what the data is, but you know what data would be. It would be 6.5 and then 12, and then the next one has 10, and then another one 7, so on. So shoe sizes, right? How much data? I don't know. There is some data and n points. You see, that data is sample. So this thing is sample. And since the text never gave you standard deviation, population standard deviation, you have to assume that this problem is 9.5. because the population standard deviation is not given in the text. So we don't know what it is. But what I can do with this is I can calculate x bar and I can calculate s, which would feed into the confidence interval calculation. Now, this problem would be much different if I had the same premises set, do the hypothesis testing knowing that sigma is equal to, right? So, and then they give it, right? So if you have sigma clearly stated in the problem, which is population standard deviation, then you go ahead and you can do the 9.4. But as you can see over here, you have the data. I didn't write the points in the data, but you have the data. That means that you have n, and you have all the xi's to find x bar and to find the standard deviation, sample standard deviation. So these guys, the data is going to give rise to the standard deviation and x bar for that sample. And now we can do the hypothesis testing after this. So now you have choices to make. A choice between z-score and t-score, and they're not the same, right? Plus, z-scores, you're looking at the z-score chart. T-scores, you're looking at the t-score chart. So they're completely two separate worlds. It is the text, it is the wording, right? The words like all or every, right? Those are the words that outline population. And then you have, when those words are not around, and if the problem is talking about the sample, where you have to take that sample as a sample, not as a population. So there are differences. And which one you're using, 9.4 or 9.5, is not a blind guess. You have to go into the word problem and you have to figure out whether they did not give you the standard deviation. If they gave you standard deviation, then it's 9.4. If they didn't give you standard deviation, then it's 9.5. Remember what the formula for t-statistic is. When you look at the formula for t-statistic over there, none of the entries are population entries. None of them. So we don't have to rely on population data. We infer, right, on where the mean should be and all of that stuff. The next part that I want, so I'll deal with probability later. I just want to make sure that I go through all of these. So also what you have to be very careful is when you have shading. So if you have this situation, just look at the z-score chart. If you have this situation, look at the chart to get some number, and then z is going to be it's 1 minus the number. No, sorry, area. It's 1 minus the number. There we go. Because the z chart is giving you only areas to the right, to the left, and if you need the one to the right, you have to subtract from 1. Now I had those interesting examples for on your exam where one was shaded like this And let's say this is negative 1.3 and this is positive 1.3. So I'll write this in blood, same. Because then you have the symmetry. They have to be symmetrical. So if you use negative 1.8, then you have to use 1.8 on the other side. How do you find the area of the shaded region? Yep.
No. If you find the negative 1.3 and the 1.3, and if it's A equals
Nope.
yeah.
Nope.
You have to add them both together.
Find
once
the
you
area
add
of
it.
negative 1.3 and then multiply it by 2.
Very good. For this particular, you're confusing it with the next example. So for this particular one, we are only looking for the shaded region. The shaded region, and the z-score chart gives us stuff to the left. You will actually figure out the z for, you will figure out area for z equals negative 1.3, and then you will double it. Because you have the same on the other side, because 1.3 is symmetric. So you find the area to the right here, and that's going to be the shaded stuff, right? And then you multiply that by 2 to get the shaded stuff on the other side. Now the next example is the one where we get to deal with the subtraction, because in this example, right, when I have stuff over here in the middle, and I have Z1 and I have Z2, this is going to turn into area 1 and area 2, and then you subtract bigger minus smaller. And then you don't divide it by 2, because it's only one piece. Right? Over here you're doubling because it's 2 pieces. Over here it's just what it is. So now, for this one, Z1 will give rise to area 1, Z2 will give rise to area 2. Right? And then to find the overall area, you go area 2 minus area 1. Now clearly you cannot exploit symmetry if you have non-symmetric distributions and non-symmetric problems. But for most of the part in this class, everything is bell-shaped curve, and so it's fine. You can just convert it quickly. I hope this answers the question thoroughly. So when you have just stuff to the left, you use the chart. When you have stuff on the right, you go 1. You use the chart and then 1 minus. And then for these two cases, the first one over here is very important because that's the two-tail test. Remember, it's the one that's not claiming more or less. It's just saying you're wrong, right? That's it. They don't propose anything. They're just saying you're wrong, and then just leave, right? So for the two-tail test right there, you have to focus on getting 1, doubling, and all that kind of stuff if you want to know the percents. What else? So then, once you understand the z-score chart well, you just transition into t-score, right, with the degree of freedom. Can anyone tell me degree of freedom? What was that?
0.
N minus 1. So it's the size of the sample, subtract 1, and that's df. Yes, degree of freedom, df. Anything else? Any problems? Yes?
Can we do like the T interval thing that wasn't on the test? Wasn't really on any of the tests that we did? Like the equation that's like T with.
Yeah, because that's all in chapter 9, and we didn't, right?
No, I think it's in chapter 8, right? Wait, what is that? Yeah, like the standardized version of variable.
Yeah, that's the Z and T scores.
How do we know to do that?
Didn't I just talk about if you have standard deviation, then population standard deviation, then you have using Z's. If you don't have them, you're using T's. Hold on. I know you're eager to get there, but
So you can't, the key on that one is if you have standard deviation of C, you don't mix T.
yes, that's in the shortest possible terms. Probability. Discrete variable. You honestly think you want to stump me?
No. No, I'm like, so those are my worst. So 4, 5, and 6, which
So-
is the middle exam, right?
So maybe I should create 2 versions of the test, one for you and one for everyone else, and put just those
Take
questions
that
in.
off of mine. Keep it on everybody else. It's my Achilles heel. So I'll be ready with everything.
Woo!
It's excitement because the winter is coming.
I wish.
Who's wishing for winter? We just got out of it.
I'd much rather be in the cold than I can bundle up. I don't have to strip down. Yeah, it's facts.
All right. Do you have any concrete examples that we could do and then move to probability?
Yes, to the test. Is confidence interval have to do with this? Yeah.
That's my answer.
I lost that.
Oh, you missed it? Ah, too bad.
The first question. A random sample of 110 full-grown lobsters with a mean weight of 16 ounces.
Lobster?
Yeah.
I set it up for you right there. There you go.
Oh, it's the lobster? Nice.
I need a lobster.
What lobster?
Don't worry about it, we got it.
The first question.
Oh, lobster.
So, the lobster. Lobster says, all right, see?
This is sugar.
So a sample of 110, so we have a sample of 110 of lobsters, and had a mean weight of 16 ounces. So that's mu 0 is 16. Assume that sigma, and here is that part. See, assume that sigma is equal to 3.5, and this triggers Z, not T.
Now I got it.
Construct 95% confidence. 95% confidence interval. Hey, who has no teeth?
No, I said you gave us the T-score.
Here's the chart.
The chart.
Yeah.
We did do the T-score formula in this again.
Yeah, you did. One of the
That's
questions.
my point.
One
You
of
wouldn't have given us the-
one of the questions you had to find the t-score looking at the chart.
Yeah.
Don't worry, I'll make it up on final. Don't
Yeah,
panic.
it's right here. For a T curve
Yes.
with ds equals 50.
Yeah, alright, I got that. I got that.
Yeah.
Stop. All right, so let's see these lobsters. Construct a 95% confidence interval.
Yes.
Oh no, this was a sample that had a. Nice. Sample had the mean, so that's x bar. All right, cool. So what do? We do that. Now, 95% confidence interval. So I'm going to deal with that first. So I have this, and each one of these is 2.5%. So now, you look at the z-score chart, right? Because area of 2.5%, yeah, area of 2.
No, it's just 1 0.
I can't count. Got it. 1.96. So the z I solved it. Z is 1.96. Great. Now, some students like to compute the error and then add and subtract error rather than writing the full formula. Because, look guys, this part over here is error. So if you compute the error and you call that error capital E, then your confidence interval is x bar minus E, x bar plus E. You do the separate calculations for it. So I'm going to write the formula here. It is x bar minus z alpha over 2 of sigma divided by square root of n and x bar plus z alpha over 2 sigma over square root of n. Now, better way to write this is that the E is z alpha over 2 sigma over square root of n and then just recast the whole thing over there to interval of x bar minus E, x bar plus E. So E is a margin of error. So you compute that first, and then just add and subtract. Subtract and then add. Rebecca, right?
Yes.
So yeah, I'll single you out.
Just to clarify,
So well, we are going to do the problem now.
I thought we just did the problem.
No, I didn't. E equals, and now I need. You told me 1.96. Times standard deviation was given as 3.5 divided by square root of 110. So now you compute E. All right, so trying to compute this, nothing works. Come on, there we go. 1.96 times 3.5 divided by the square root of 10. I said 3.5. And I have the syntax left. Let's just go home.
Should be 0.64.
Oh.
0.65. 0.65.
I got... No. 0.65.
Right.
0.65. So now I have that x bar is 16, so it's just 16 plus 0 minus. Oops. Now it's spreading. 65 and then 16 plus 0.65, which is 15.35 to 16.65. There we go. Ounces. So instead of calculating this twice, guys, right? Because if you write everything like this, you have to run this to calculator and then run it again. You can define that as E, as error, and then just compute that part, just add and subtract from mean and done.
That's exactly
I'm gonna
what
leave
you're
now.
doing.
All right, and that's that. That was the first problem.
What's the final answer?
The interval.
I got 15.14.
We are 95% certain. You have to write the sentence for this one. We are 95% certain that the mean population for these lobsters is between these two numbers.
What the hell? Just because. I have different numbers there. I have
That's because you're round. It's
Oh,
rounding.
you're okay. You gave me the credit, so that's okay, right?
Do you want me to take it away?
No,
then?
I don't want you to take it away.
All right.
But I don't want to get it wrong down the road.
Then no complaining.
I'm not complaining.
What down the road? There's just a Thursday and that's it. There's no more road. It's just there's a road stop block, whatever it is.
You know what I'm trying to say.
Any other questions, concerns? We'll get to probability. Let's just get this first out of the way, because probability is so different than, right? For probability, we have the cards, we have the dice, we have the events, we have the conditional probability with the chart, right? And none of that stuff works with everything here, right? So, and then expected value, we have to do that one as well, expected value. So,
P of X, A given B, stuff like that.
yes.
So good stuff.
So let's first see if you guys have anything else regarding the non-probability stuff first. Everyone is good. Now we're going to close this part, put this line, put another line, and another line. That's 3 lines. And then we are going to say probability. So some questions will come for probability. So what are the important aspects of probability? First of all, that probability is frequency divided by number of observations, right? Probability is always between 0 and 1, which is 0 and 100%. And probability is telling us how likely it is for an event to happen. Now, we have the sample space, right? Sample space. So sample space contains, let's say, all the marbles or all the cards or all the people that you want to pull at random. So whatever you are observing, sample space is the collection of everything you have. That's actually your universe. It collapses. If I'm asking you to pull a card from deck of cards, you are not considering cars. You are not considering trees and people. You are only considering the deck of cards. So your sample space is ace of spade, and then 2 of spade, and 3 of spade, and 4 of spade, and you go for all 52 cards, and that is your sample space. Now, how likely is to pull a card that you want? Well, it's going to be the amount of, like, the frequency of, so how frequent is the thing that you want to get out of the sample space, which is everything that exists. So if I want to pick a red card, well, half of the cards are red, so probability of picking a red card is 50-50, right? It's 26 of 52 because 26 cards are red and 52 cards altogether. Now, the trick is that, you know, every time when you pick a card, yeah, it's 50-50 to pick a card, but you will 100% of the time pick one of the colors, right? So it's repetition in probability that gives us actually these numbers to smooth out and give us values. So maybe you are going to pick 3 black cards in a row. You pick a black card, and then you pick a black card again, and a black card, and you say, well, wait, is this deck just black cards inside, right? And then you turn the deck around, and it's not, right? It's just, hey, probability is 50-50, and you just happen to pull 3 black cards in a row. So sample size and the sample space, they're important, right? And then they define, right, in which space you're operating. So now for the probability, we have all of the rules, the addition rule, the multiplication rule, and then we also have the conditional probability and joint probability and all of that good stuff that involves contingency tables. Now, we also have to understand mutually exclusive, independence, replacement, how to pick something, right, with replacement, without replacement. There's a lot of different things that we can consider in probability. So, actually, probability is a branch of mathematics that it's not statistics, actually. So when you go to 4-year school, you have applied mathematics, and then you have probability and statistics department. So they're separate in that department, just like applied math breaks down into, you know, financial math or waves or fluid dynamics and so on. So probability, that's why probability chapter over here is has its own heading. So now, what is the probability to pick a red card? It's going to be 26 out of 52, and that's going to be 1/2. But now the question is, what is the probability to pick 2 red cards? Without replacement. So we have to specify no replacement, so we know that to pick the first card, it's going to be 1/2, but to pick the second card, it's going to be 25 over 51. So this would be the probability to pick all of these cards. So let's see, so this is 25 over 102. So probability is 24.5%. So 24.5%. So you have 24.5% to pick 2 red cards in a row without replacement. Now with replacement, which means put it back, pick 2 red cards, are you expecting bigger or smaller number than 24%? Why higher? Because you put the card back, exactly. So to pick the first one is a half, and then to pick again it's a half, so it's a quarter. So it's 25%. So it's a 0.5% higher probability to pick without replacement. Because remember, if you're picking 2 cards and you pick a red card, your deck has 1 card less, but it's not just 1 card less, it's 1 red card less, right? So both numbers go down. Right? This one goes from 26 red cards to 25 red cards, and this goes from 52 total cards to 51 total cards, because without replacement, the card we picked, we didn't put back. But now, going to this one, right, with replacement, you pick a card, hey, it's red. Then you put it back, shovel, shovel, you pick again, and you pick another red card. So that's why it's half and half, because you took the card you picked, you celebrated, you put it back. That's with replacement. So you have to be very careful when you're reading these problems. Actually, you know what? Just be careful until further notice when reading the word problems. Just be careful. So I don't have to repeat it every time till you're told otherwise. Read the question and answer the question. Now, what we have is the probability of picking a card that would belong to 2 different events. See, there is an event that card is a face card, and an event that the card is a, let's say, red card. So we have to worry about that as well, because we don't want to double up on some of the numbers that happen there. Let's pick a card. Pick a red face card. So what's the probability? So that's the thing. Pick a red face card. Red face card. How many are there?
Are you red faces?
Yes.
8.
Are you including aces?
No.
So 6.
6, right? So you have heart, king, jack, and queen, right? And then diamond, king, right? So hearts and diamonds. So, and 3 faces each, jack, queen, and king. So the answer for this is very simple. 6 out of 52. We know that, right? Now let's take a look if we can figure out the probability using the rule. So probability to pick the red card and the face card would be what? Well, probability to pick a red card is 26 in 52. Plus what? Probability to pick a face card is?
Isn't it red and face? Wouldn't it, if you're doing the addition, then you have to change it to all red or face?
Yeah.
So wouldn't it be just 6 over 52, not any addition?
No, we already have the answer.
Okay, so you're doing another problem.
No. I was doing the same thing, just maybe this is just going to confuse you. Okay, it's fine. You're right. You're right.
I mean, it's an R and F, so I'm assuming that's just
Yeah.
still.
Let's do the OR. So now, pick red card or face card. What's the probability of red card? 26 over 52. Plus, what's the probability of face card? 12 over 52. Now, we have to subtract the 6 over 52. Right? because this one over here for red cards includes 6 faces, and this one over here includes the same 6 faces. So now I take one of those away. So this is 32 or 52. You don't need the. Oh no, we can reduce it by 2. So that's a 16 by 26. Reduced by 2 again. It's 8 over 13. So 8 over 13. And let's take a look at contingency tables. I know how much you love it. I just want to steal a... So big. We worked out all of these examples. Everything that remains is really huge. So I guess, what is this one? Self-concept and psychedness. Self-concept and general view also. Alright. So let's take a look at this. I have to draw this this chart. The table of values. So sighted, blind, and total. It's V1 and V2. And on the other side over here, we have a high, moderate, and low. So 1373.14. $340.1760. $16,113, $31,160. So that's the chart, finally. All right, so what we have here in the middle, with a thick border around, those are called cells. And then the numbers on the outside are totals. Now, we did stretch this over 2 sections because book said so. But you read joint probability and marginal probability and conditional probability off of the same chart. So use it for joint probability, marginal probability, what is the other one? Conditional, thank you. So joint probability, marginal probability, and conditional probability. Now, joint probability, you should write this in your notes, and I will. So guys, joint probability is when you take one of the cells divided by the grand total, in this case by 100. So cells are the ones that are highlighted in the data, the 13, 73, 14, 3, 4, and 7. No, 40. 3, 40, and 17. There we go. This is 40. 3, 40, and 17. Because 3, 4, and 17 can't add to 60. Just notice that. Alright. So joint probability is when you take a cell, so one of the 6, and divide by the grand total. That's called joint probability. So I want to know blind moderate. Blind moderate is 40 over 100. 40%. Blind moderate, 40%. So when you are dealing with the joint probability, you take whatever cell is outlined in the text, and you just write that cell divided by the grand total, and then you get the decimals, you get the percent, and so on. Marginal probability. Marginal probability is when you take a number from a total column and divide by the grand total 100. So I want to know the probability of blind. Probability of blind is all blind, which is the entire row. So 60 divided by 100. That's why it's called marginal, because these are margins, right? The end. So joint probability is joint because it's the cell between the two, right? They join there, divided by grand total. And then you have the marginal probability, which is the margin divided by the grand total.
I'm losing the grand total.
Grand total is 100. Grand total is the corner.
But it doesn't add up to 100.
It should be 160. Yeah.
What did I write?
Moderate total is 130, but the grand total is 100.
It's 160. Please pay attention.
You said marginal probability when you take the number. What was it?
Marginal probability is going to take one of the totals and divide it by the grand total. So marginal probability takes a total, one of the totals. So 100 or a 60 or 31. So it takes a marginal number, right, the total, and divides it by the grand total. And finally, conditional probability is the one that is tricky, right? You restrict yourself to row or a column, and then you operate in there. You don't use the grand total ever for conditional. So let me color code this now. So here is an example. Probability of V1 and S3. So that will be joint probability. V1 and S3 is 14 over 160. 14 divided by 160 is 0.0875. I'll just say 8.8%. So that would be joint probability. You pick a value and then you do that. All right, let's go with the next. Marginal probability. Marginal probability would be if I'm asking for probability of a blind. So that's V2.
Yeah, but you just said for conditional, you never use rank rule.
Exactly. I'm not at conditional yet. So I'm doing marginal. Marginal probability, so blind, that's going to be 60 divided by 160. So that's 6 divided by 16, that's 3. $0.375 or 37.5%. And that was that. And now for conditional probability, let's use yellow, I guess. For conditional probability, I am going to ask for probability of blind given high. So V2 given S1. Now, remember what I said, given S1. So S1 is either the row or the column that gets highlighted and nothing else exists. So now I have to highlight S1. S1 is this one. Nothing else exists. So what's the probability? Probability is 3 divided by 16. Yeah, 16 from the margin, right? 16 from the margin. So what's 3 divided by 16? How much?
0.137.
Thank you. So that's about 18.8%. Right. So joint probability, marginal probability, and conditional probability, they all use contingency tables. The only thing that I can do here to spice it up a little bit is if I again erase some of the entries in the chart, so you have to repopulate those using additional subtraction. And that's that. I hope you're not disappointed. Now, we do have some of that from chapter 5, right? The discrete, which is also tied to probability. When you look at the weighted averages and the expected value.
I remember doing the quizzes for this exam, like part of it, and I know we were given 3 factors, like A equals something like no less than 5, and then B would be like in between 2 numbers, and C would be like anything random, and it would say, oh, find the probability of A given not B. Like, would a problem like that be on the exam?
If you really want it.
No.
I don't want it.
Because
But you know what I'm talking about?
yeah, but it's dealing with the logic, so
It was more for the cards, not like.
yeah. So you that's it's just for you to play mentally with the sample space and figure out when it says non-face card, right?
Yeah.
So you can non-face card. Then if I have 13 pursuit and 3 face card, and I have 10 that are not face, right? So use that number. So it's more chasing things around.
Is using the binomial probability formula?
It's coming up.
Are we gonna get the deck of cards?
Yes. Deck of cards will be displayed. Yes, deck of cards will be displayed. You will get the T-score chart and the Z-score chart. No. All right. So what's left is to talk about expected value and to talk about the binomial probability with the Bernoulli Trials. Remember the one that no one liked, and it's my favorite?
With the furry little ones.
With what?
Yeah, on the
There
test.
was, on the test, it was like, how many furry little ones are female? I was like,
Yes.
Oh, yeah.
yes.
Whatever they have over there.
I did the formula and I didn't know it was like N or like.
That's the one you said we're not friends anymore because I did 7 minus 3 is 5. Because
Yeah.
I was racing through it.
I think it was
Oh, little fur. I said little fur balls.
Fur balls. Okay, fine.
Fur balls,
Fur balls.
yeah.
It was like really expensive and
That was
The little fur
bad.
balls being female.
Not my brightest moment.
Yeah, it's a litter. Yeah, they always have like that many. That's so cute.
double triple. It was a double spawn. Cats.
No, no.
Okay, so we have the expected value. And you use this to predict the outcome if you know probabilities and involved and so on. So this is used to figure out, let's say, the busy telephone lines for technical support. It's used to figure out to dispatch police and emergency services or pizza, and then a lot of different things. Also is used by casinos to figure out the expected value, the expected outcome on average, so that they know that they will not be losing money ever. Because the trick is to have the good game for casino, from their perspective, is the game that looks fair, but it's not fair. None of the games on casino are fair. That's that, because, yeah. So what is the expected value? Expected value is the mean when we take the summation of x values and multiply that by the probability for each discrete variable. And the best way to understand this is to say, okay, let's flip a coin. Let's flip fair coin. That's important. So if you are flipping the fair coin, tails will have the probability of 1/2, and heads will have the probability of 1/2, right? So that's the outcome and the probability. So now, if you think about this, right, and you calculate the expected value for the game would be like this. So let's make a game now. Game says, for heads, plus $1, for tails, minus $1. So now I'm going to make this chart. Again, I have heads and tails, and now I have heads is +1 and tails is -1, and then I have the probabilities, which is each one is 1/2. So now, what do I do? Well, we do the formula from the top. What's the expected value? Expected value better be 1/2. So I have 1 times 1/2 plus -1 times 1/2, and we get 0. So what is the expected value here? You're expecting $0 to make $0 because you have 50-50 probability. It's fair game. And this is why casinos cannot afford a fair game. Because that means that if they're infinitely open, and they're open 24/7, they're not making any money. Because the expected value of earnings for playing this game is 0. Right? You might lose 10 times in a row, and be $10 out. But if you play forever, no money in, no money out of your pocket, on average. Now what I'm going to do is I'm going to tilt the scale now. I am going to say that the game is still the same. I have the heads to gain $1 and tails to lose $1. But what I do is I temper with a coin so it's no longer fair. And you go and you flip, and most of the time it's going to be in my favor. So heads plus $1, tails minus $1. And here's what I'm going to do now. Instead of having half and half probabilities, I am going to put smaller probability for you to win and a bigger probability for me to win. Right? Because you are gaining $1 if you flip heads, and I am gaining $1 if you flip tails. But the coin is now no fair. It's heavier, right, on one side so that the other side can show more, right? Because the heavier side, the gravity is going to pull down. Or whatever way you figure out to cheat. Doesn't matter. So, when you calculate the expected value now, you have $1 for 0.4 plus a negative $1 for 0.6, and you can see that on average, casino is making 20 cents per flip. On average. So sure, you're going to flip, you are going to get heads, you are going to get your $1. You're going to flip again, and you're going to get heads, and you're going to get the $1 again. And then you might lose the next time around. See, the trick is that you don't know that you are flipping a coin that is not fair. So if I just let that game go forever, I am guaranteed to be making 0.2 per flip. And that's how the whole thing works. So that's, I told you the reason, right? The roulette game has 36 fields, 18 are black and 18 are red. And then there's the additional one, the 0 one, the green, right? So that's the one that slightly tilts towards the casino, and casino always makes money, regardless of what you do. Now, what can I do with this? Well, I can just go and say measure the amount of times for the ambulance to reach a certain location, or firefighters, or police, or like any kind of emergency vehicle, or train schedule, bus schedule, like all of these kind of things, and then also work with workers and setting them up, and so on. So that's that's the expected value. And now we also jump into the Bernoulli Trials with our probability. So what are the Bernoulli Trials? The Bernoulli Trials are the ones where you can have two outcomes. One outcome is either true, your outcome is either true or false. So you know when you are answering multiple choice questions, you either get it right or you get it wrong. There is no partial credit or any of that stuff. So it's right or it's wrong. The light is on or off, right? You are normal or not. I don't know why I pushed that way, but I figure of speech. So in Bernoulli Trials, also probability of success needs to be the same for each independent measurement we do, or experiment, or whatever you want to call it, flip of a coin. So when you flip a coin, it's a 50-50 chance to win, and then you flip it again, and you flip it again, and you flip it again. See, the outcome of the coin, when you flip it next time, does not depend on the previous flip. Because the previous flip had the heads and tails on the coin, right? You got whatever you got, and now when you're flipping it, well, you reset the whole thing, and you're starting from scratch. It's much different than if you pick a card from a deck and you don't put it back. That cannot be Bernoulli Trials. Because when you pick the card out of deck and set it aside, well, first of all, you either won or you lost. Sure, right? You have the probabilities assigned to that. But the trick is that if you don't put the card back, the probability of winning is different, and that's not Bernoulli Trials. So you have to make sure that you have the same probability of success and same probability of failure as you move from one trial to the next. So for Bernoulli trials, the probability was given as the coefficient, trying to remember which letters we used. It was X, and choose X, I believe. I can't remember which letters we used.
Yes.
And it was a probability of success. So that's, let's say, S to the X, and then failure to the, well, 1 minus S. That's a failure on N minus X. So S is a probability of success. That's that. So you have the probability of the failure, success, and probability of failure. It's important that those two probabilities remain the same during each independent trial that you do, and it's important to have only two outcomes, true or false. And you succeed with certain probability, you fail with a certain probability, which remains constant from one trial to another. So that's that part. And with this, you can find some cool probabilities. You've seen that to pass a multiple choice exam, right, with 4 choices, just randomly guessing, was less than 1%. You remember that calculation? It was scary, right? And that was you scoring any of the grades in 70s, 80s, 90s, or 100, right? When scoring any of the grade higher than 70, you had less than 1% a chance of guessing. So Bernoulli trials really show a lot of this cool stuff. So I just want to see if I can find.
So the one from the question from the exam with the tax.
Yes, do you have it?
Yeah.
Because I was about to go look for.
Wait, Professor, wasn't it like the P to the S? Yeah, it is.
Doesn't matter which letter you use. Now I'm looking at this, and yeah, I use P. I used S as a probability of success. So S. When I learned this formula, I learned it as S to the X, F to the N minus X. That's how I learned it. Because S stands for probability of success, and F is the failure, and you know you're supposed to do 1 minus. But we just...
Yeah, I remember there were like 7 kittens.
Yeah, I completely blanked.
A cat litter has 7 kittens.
Yeah, that was so hard.
With kittens?
Yeah, I thought it was
Are you kidding me?
I mean, good one.
All right.
That was quite difficult. Look at what I did. Look at the work I did.
I don't want to comment on it. I commented the first time I saw it, and I want to see it anymore. All right, ready? So a cat has a litter of 7 kittens. All right, great. N equals 7. Find the probability that exactly 4 of the little fur balls are female. So X equals 4 are female. So for cats, they say assume that probability of a male and female being born is roughly the same. Great. You are looking for a female kitten. When you see one, you label that as a success. When you see a male one, you label it as a failure, right? So what you do is you will say that probability of success is a half, and probability of the failure, which is 1 minus S, is also 1/2, because as I said, when you see a female kitten, because that's what they're looking for, that's called a success, and that's 1/2. Well, the male in that case would be a failure, and then they would, right. So now, what do we have? We have that the probability of exactly 4. So that's correct notation, x equals 4. It will be 7 choose 4 times 1/2 to the 4, and then 1/2 to the 7 minus 4, which is 3. So what do we have? We have 7 factorial divided by the 4 factorial times 7 minus 4 factorial, which is 3 factorial, times 1 over 16 times 1 over 8. 7 factorial is going to be written as 7 times 6 times 5 times 4 factorial, which cancels, and then 3 factorial is 3 times 2. Well, that's 6, so that cancels. 1 over 7, right? So that's 16, 32, 64, 128. There we go. 7 times 5 is 35, divided by 128. 35 divided by 128 is 0.273. So there is a 27.3% chance that exactly 4 are female furballs. Yes?
Could you write out the formula for N over X again? Like for the order?
Oh, sure. And choose X?
Wait.
No. What happened? 7 minus 4 is 3 factorial. 3 factorial is 3 times 2 times 1.
You just split it up. You just did the factorial of 3, because it's only 3 times 2 times 1. So he just left out 1, because it's just the same thing.
I didn't write 1.
Yeah.
And then 3 times 2 cancelled with 6 on the top, so only 7 times 5 remains. You have to expect, this is my favorite question. Like the all statistics, Bernoulli Trials, my favorite question, and then second favorite is the intervals with T scores, right? Because you don't need population data, you don't have it. You have sample data which you got from your sample, and then you can. So I like realistic stuff.
So both of them can be in the binary.
Well, yeah. Well, that's why we did the list, and we did the detailed review for those two, right? Yeah. You must expect contingency tables, guys. It's 100% with all the probabilities we talked about. So you must have that. You must have some vanilla probability in terms of looking at either the dice or the cards. You must have the interval of convergence. Sorry, confidence interval. Intervals of convergence is calc too. So confidence interval. You have to be able to look into the Z chart, get the area or get the Z depending on what you need. The T chart the same. And then don't forget the degree of freedom for the T chart. You need that, n-1. And then what else? There was something else very important. Well, everything else. Margin of error, right? So margin of error. You know the formula for Bernoulli Trials. I told you Bernoulli Trials is going to be there. And
like the very first test, how like a lot of us got wrong, like the simple and mean everything, because like we didn't include the middle one. So when you're like splitting in half.
Oh yeah, 5-number summary.
All
And
that. All that.
and there has to be, yeah, I forgot about that, at least one histogram or a pie chart or something to either read or create, because it's important.
Can it be a histogram instead of a pie chart? By request.
Pie request. No.
It's not technically driving, right? So just like, you don't know about it.
About what?
Exactly.
Yeah, you gotta know. Any other questions, concerns? Yes?
Well, maybe do a tree diagram.
Yes, the tree.
Can we go over that?
Sure.
Because that, I don't know why.
The tree?
Just draw 1 and 1.
Guys, look at outside, it's green. We have to commemorate that.
No.
So,
Yeah, how is there a tree diagram if there's only 13?
that's a joint probability, picking the part. Right?
So it might be a 2-part.
Let's say group of 4 people, and you're supposed to pick president and vice president. Right? Draw the tree. Yeah, let's go. Tree. Yeah. Tree. Specs are 4 people. Need president and vice president. So,
A small tree with 4 people, it's like 1 branch.
well, look, there is a branch for president and a branch for vice president. The probability for someone to be picked as a president out of 4 people is 1/4, right? And then someone else to be chosen as a vice president, well, now you have to think a little bit, right? You choose president first, right? So that took 1 person away. So now 3 left, right? So to pick the vice president on the branch, we have to now have 1/3 probability.
Isn't that the next branch, not the one that now?
Well,
They would both be the same for the first one, and then they break out.
that's for a different type of the problem, but yeah, that's for a different type of the problem. Because I'm picking 2 categories here. Right? We can, okay, let's not do then.
This is really confusing.
Okay, let's do marbles.
Okay.
Let's go with marbles. So erase everything that you have for this. Let's do marbles. We have 17 red and 9 black marbles. Draw a tree for 3 draws without replacement. All right. The first draw, you either pick a red or you pick black. What is the probability to pick red? 17/26. What's the probability to pick black? 9/26. So as you can see on a first draw, I'll put first over here. That's a first draw. For the second draw, you can pick red or black on both of these.
I have a question. Why would this is gonna probably gonna roast me, but like, why? Okay, why isn't it like the probability of picking a red? Why isn't it like 1 out of 17? Is it because they're all together?
Yes. So you have 17 red and 9 black marbles, and you put them all in the same hat or the same bag, and you mix them. So the total of marbles that you have, whether they're black or red, it doesn't matter, is 26. And since there are 17 that are red, then the probability of picking a red one is 17 over 26, which is how likely is to pick divided by all, which is 26. And that's the first formula for probability that I wrote, like F over N, right?
So on the first draw, you haven't actually drawn anything.
I did.
What'd you draw?
Either red or black. I have both
Really?
possibilities.
Didn't take any away?
No, now well, they're all present as I am picking. This is where I picked.
Okay.
So now from this point on, I have 25 in a bag.
Okay.
So what's the probability to pick red again? 16 over 25. Good. And to pick black? 9 over 25. Good.
So it's like,
Because the top branch picked red, so all of the black marbles are still in the game.
How do you know that?
Because I picked red.
How do you know you picked red?
Because it's R.
Yeah, you have 2 options.
It's 2 options. I either pick this one or that one. I can't pick both of them, right? So these probabilities will pertain to the probability that I picked red. These probabilities will pertain that I picked black the first time.
Gotcha.
So when you start here,
So
you haven't picked anything
took
yet.
red.
And these are the chances to pick one or the other. You will pick one.
Right.
And then it branches. That's why it's 3. Because it's branching the possibilities, right? You have, it's making a choice, right? You go to Starbucks and you have 15 different choices. You make one choice. Now someone's like, why didn't you try, right, the other one? Well, no, because I picked this one, right? That's the thing. So the top R is the R that is,
So you pick the red.
we pick the red, and because we branch it off of that one, that's why it's now 16 reds, but still 9 black.
Right.
Now we go on the bottom one and say, well, we picked the black. That means that still 17 out of 25 reds in a game, but it's 8 over 25 for black. Now that was the second draw. We're going with a third draw in each one of these branches. And each one of these branches into red, black. And now to follow this, a little bit trickier, but we can do it. All of the denominators have to be 24 because we already picked 2 marbles. Since we had 26 marbles altogether, and we already picked the first 2, and we are working on a third one, so all of the denominators are 24. So I'm just going to set up all the denominators. And then populate the numbers. Following the first branch, I pick the red, I'm picking red again, so that's 15. Black was never picked, so it's still 9. Now I'm going to the next branch down, and I see that since on the first draw it was red, so that means 1 red less, but on the second draw was black, so that means 1 black less, so I still have 20, so I still have 16 reds on that one. And for black I have 8. Because 1 was picked already. Did this make any sense? Whatever, huh? The first one. Okay, so let's go now with the next branch over here. The next branch is black, red, and then red again. So let's see. I picked the black, then I picked the red. So both of them went one down. So red is going to be 16, and this one is going to be 8, because I picked one red and one black already. So both of them go down by 1. The next branch is going to be black, black, and then red, black. So first one was black, second one was black, and then all of the red ones are still in the game because I picked the black first time and I picked the black second time. So all 17 of red ones are still in a draw. And then and now this one goes 9, 8, and then 7.
It should not be 16.
Wait, question, don't some of those branches...
Hold on, one by one, whatever.
So on the third branch, you got 16 over 24, but you picked black again, so shouldn't it stay 16 over 24?
Are you talking about this number here?
One down. One more. Shouldn't that be 16 over 24?
Why?
Because black, black.
Yeah, but it's red. I have 17 red ones, and I never picked red one. The problem. This is what's still in the hat. The picking is done here. So these are the numbers that are telling me the probability before I do it. You see, over here, this is the pick, and these are the chances to pick.
Yeah.
So you can have. You picked one, and now you have 25 marbles. You picked another one, now you have 24 marbles, right? When you pick another one, you have 23 marbles less, right? But you haven't picked yet. This is the probability to pick these, not afterwards.
Wouldn't you just do another set of 2 branches instead of 4? Because it's weird, because that's how I get on the exam.
Okay.
Maybe I should.
I'm just saying, because if you look at it in regards of the tree, the probability of, alright, so you went from red to red, whatever. Then the next one is red or black. But the probability of choosing a black from those 16 out of 25, that doesn't make any sense. Instead of it's not
Here we go.
It's not
That's why my question is, don't some of these combine?
Yes, they are, but
Okay.
doesn't matter. Yeah. All right. So now, let me show all possible combinations here. The first one is red, red, red. The next one is red, red, black. The next one is red, black, red. And red, black, black. And that's the first 4. Then we have black, red, red. Black, red, black. Black, black, red. And black, black, black. And these are all 8 possible, it's 2 cubed, all 8 possible ways to get these. Now, what you're saying is, can I combine these? Well, yeah, if I ask, to pick 2 black, right? To pick 2 black, well, this one has 2 black, 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 so it's 4 out of 8. 4 out of 8 have 2 black.
So you're saying if the question says 3, right? Then we would have to do a 4 out of the question. If it's 2.
Then you would stop with these ones.
Yeah, then we would stop there. Okay.
So what would be for number 8 of this exact exam when we're given those in regards to heads and tails? So the probability distribution of the random variable x? How would you go about that? Yeah, it's like a coin is tossed 4 times, 16 equals.
Yeah, that one. Wait, which one was this one? Oh, this one? Yeah, I didn't get that one.
When a coin is tossed 4 times, 16 equal likely outcomes are possible as shown below. By texting out the known number of tails obtained in the 4 tosses, find the probability distribution of the random variable x. Yes, so that's just the probability of probability distribution. So the answer is looking for the chart. It's not looking for if you look over here, this is my chart just started. So what do I have here as the probability? I have red, red, red. I have this times this times this. In your case, it's half times half times half, so 1/8, right? But over here you have this times this times this for the first one. This times this for the second one. And you create each one of those probabilities there, and then you combine those that have 2 black or 2 red, whatever is asked over there, right? So you have to create. Yes.
Yeah, if you have the green or the colored one, it's number 8, but it's the one with the coin toss. It was like it's tossed 4 times, 16 equal likely outcomes.
Yeah.
So what was the answer?
The answer is to make a chart, the one that I started here. You make the chart, and then you multiply these numbers along the way. Since you were tossing a coin, each one of these was a half, so it was easy. Right over here, these numbers are more involved, so you would have use calculator. The answer should be, could be or 3/8, depending on how many of those you had.
So once you write off, like let's say red times black, you multiply all those. Once you get that number, when it asks let x denote the number of tails obtained in the 4 tosses, you just add whichever ones have the tails in them?
Yes.
Okay.
So only one would be on all heads. Everything else would have at least 1 tail or 2 tails or all 3 tails.
Okay.
Just replace all R's with H's and all B's with tails, and you have the same thing for 3 tosses, right? But over there you have the 16, so. All right.
What about the birthday question?
The birthday question?
Yeah,
Oh, the birthday question. Oh, I love that. Was, yeah. I said, let's pick something simple. Everyone knows. I was thinking, like, if I do the lottery or if I do the license plate, everyone is going to go nuclear, right? Let's pick something that everyone knows, right? Which is probability of a multiple birthday. What are the chances that 3 people in random will have the same birthday, right? That the question?
Yeah.
Good. So, which, right?
I did like P of 1 times P
That was the best way
I
to
don't know
approach
where I got this from, but
All right, so can you read that question out loud?
okay. Find the probability that 3 randomly selected people have the same birthday. Ignore leap years.
Perfect. What does it mean, ignore leap years? This, no 366, so 365, right? So, 3 random people have the same birthday. So, let's pick one person here who's my volunteer to share the birthday. What's the birthday? Yes. I'm sorry?
March 2nd.
March 2nd. So that will be 3-2, right? Now, I'll call you the first random person, okay? Because you volunteered, so that's fine. So, random person. What's your birthday? A random person.
I was picking 3/6.
Okay, so March 2nd is random. So, probability that your birthday is on March 2nd is 100% because it is. So that's the first. You have 3 people to worry about. Hold on. You have 3 people to worry about. He's the first person times the second person times the third person, right? So the probability for the first person for birthday to be on March 2nd is 100% because that is one person. Now, we are going to pick random person, random person, random person, and I'm just going to say, what is the probability for your birthday to be on that same date? 1 over 365. Now, I am going to go to the next person because random person, and I asked you, right? But now I jump to another random person and I ask them, are you related?
No.
Are you twins?
No.
Right? So now, what is your probability of a random birthday?
1 over 365.
And you just multiply these numbers out, and there's your answer. Done deal. Yeah. So the first person has definitely a birthday on that day, right? Because you have to start somewhere. And then the next people is just 1 in 365.
Okay, so in my defense, the question, like, I didn't understand what the question meant. Like, random birthday of those 3 people. I thought it meant like any 3 people had one, like you pick a day out the hat, and then if they had that day as a birthday.
I think the thing is like same. It's saying like I guess I get it because it says like that out of 3 people, like what's probably that like one of them will have the same birthday.
But it doesn't say out of 3 people. It says 3 random selected people. So like I was thinking like, all
Yeah,
right, so
3
say-
random selected
like,
people. That's what I did.
October 1st, and you go out to the street and say who has that. Like, ask one person. What's the probability of that? You know.
No, but they have to have the same birthday. So you have to start with knowing the date. You can, right? And that's the person that has the birthday on that day. So you can rephrase that question. What is the probability that the other 2 people will have the same birthday as me?
Yeah, see that if you would have said that, then I would. Oh. Okay.
Wait, like what would have been a better like way to reword it? Like would you say like if it was
What is the probability that another 2 people in this classroom will have the same birthday as me? That's another way to ask
Yeah,
it.
that would make more sense.
What's
Yeah.
the right answer?
Same answer to this.
Just add multiply them.
No, I got 7.5 times 10 to the negative 6.
Good.
What's the answer?
Yeah. It's a very, very low probability.
Small.
Yeah. So generally in a classroom of 30 people, you might, you know, when the classroom is full with 30 people, chances are that we're going to hit the same birthday. But
Can I just write 0.00000?
yeah, you can.
7 something?
You can. All right. So that makes sense now. Now you can play this game and see how highly unlikely it is to win a lottery. If you have the, what is that, pick 4 or pick 5? So let's do pick 4. And the digits are 0 through 9 for pick 4? Okay, let's play.
1 to 50 or something.
Why? I can ask Google.
I don't play things I can't win.
True. I like that mentality.
Why should I waste
I don't
my
get into
money?
arguments
I'm
like
gonna,
that.
I work hard for that money. I'm just gonna.
Yeah, but you can double it or triple it at 190.
Okay, what are my options? What am I on?
We can find out, but you know, the fact is there is a chance.
What is my statistical odd?
But the point, there is an odd, so you're
There
good.
is. It's horrible.
That's worth it. It's worth it.
It's not.
Don't listen to me.
Trust me,
I
it's
bet
not.
500 on this one. Yeah.
Let me get some.
Very dark day. Dark 48 hours.
All right, gameplay. To play pick 4, each number must be chosen from a separate field of consecutive numbers from 0 to 9.
No, that's not. This one.
Yeah, okay. So, to pick 4, let's see what is your probability to win. Ready?
Yeah.
So, pick 4.
75.
You are picking digits 0 to 9.
Oh, 0 to 9?
5.
4.
3, 2. 3 and 2. 3 and 2.
Hang on.
You can spray this.
So, hold on. You are picking 4 numbers. So here it is. One number, another number, another number, and the last number. That's pick 4. Now, I don't care what is the number that is there. You have a target number, right? Came to you in a dream, right? And it's 3105. What is the probability that they are going to pick that number, right? So 3105 came to you in a dream. You wrote that on a ticket and paid for it and whatever, right? I don't know what the game goes, but that's the target number. What is the probability that that number is going to pop up? 1 over 4?
1 over 9 times 1 over 9 times 1 over 9 times 1 over 9.
What is the probability that you are going to pick a 3?
1 over 9.
No.
You said 0 through 9.
Yes.
0, 1 over 10.
Ah! So there is 1 out of 10 probability to pick a 3. Great. Let's go to the next number over. What is the probability to pick a 1?
1 over 10.
Is there
1 over 10. Nice.
zero an option?
Yes, it is.
Oh, it
It
is.
says 0 to 9.
You tricked me.
What's the probability to pick 0?
1 over 10.
1 out of 10. And then? Probability to win is 1 in 10,000. Beautiful. That's how likely you are to pick 4. Pick 6, it's going to be worse. Pick 5, it's going to be worse. And then they add the stuff with the Powerballs and this and that, right? It gets worse with anything that. So, and then you have numbers for lottery that are bigger than 0 to 9, right? It goes into 10s and 20s and 30s. You can never pick. Mega Millions, right? Why the Mega Millions? Because millions of people put in money and they lose. Now someone gets lucky, right? But guys, you have to understand that that's 1 in a million. It's not, so that's how these games are played, right? So it looks like, oh yeah, I have a good chance because all I need to figure out is 4 numbers. Yeah, good luck. You know when you are guaranteed to win? You are guaranteed to win when you buy 10,000 tickets and write all of the numbers that you can have. Then you are allowed to win. Because the denominator there tells you the sample space. That's all possible combinations that you can have. So you are going to go to the place and you're going to buy a ticket and put 000. Then you buy the next ticket, 001. Then the next ticket, 002. And you buy all of them and you are guaranteed to win. But then multiply the cost of buying 10,000 tickets and the payout that you get on it.
That's going to be worth it.
Is it?
If each ticket's like what, $5, $10?
$5.
All right.
So that's $50,000 to buy it.
And you'll win millions, almost a
And
billion.
get taxed on that.
You still have a profit.
And then you have to claim it as income gain
And then you're still
at the end of the
profiting.
year.
You're still profiting. no matter
More
what.
tax on top of that.
That's okay.
No,
Still
it
profit.
isn't.
Instead
And
of
if it puts you in the
200.
if it puts you in the bracket that you don't want to be in, it's even higher tax.
You're still profiting.
Trust me, it's not worth it.
I would have
The price of a single play shall be 50 cents.
For what?
50 cents
For the ticket?
for a ticket, yes.
What's that?
It's 50 cents for a ticket.
Yeah, it's $5,000, yes. So you go, you buy $5,000 and then
sit down and tediously write down.
There you go. I just made you rich. There you go.
Yeah.
To be set for life.
Is that even legal? I'm pretty sure you can't buy more than like a certain amount of like.
Let me see.
In New Jersey too. So like,
You can buy as many.
This ain't
are you
Costco.
sure?
Please let me know when you got the 50 grand to buy all those tickets.
If we all pull
You
together.
got 50 grand
Yeah,
already.
right.
Let's see what
The cashier who does that, it should probably be be so bad.
Yeah, I know.
Wow, you're gonna go for
I don't know if there is a cap on it. I can't. It's just I pulled up a document, a PDF that it's actually the government one on the official game rules, Pick 4, and I believe that I skimmed over that there is a cap on how many you can buy, which kills that thing. But yeah, don't worry, they thought of everything.
You can get like that for numbers or something like. Let's say you got 5,000.
I can't. They have some.
No, but I'm just
But
saying.
there's no possible way to determine how many you purchased. You don't put your name on the ticket.
Yeah.
And you can go to multiple places.
But I don't think that actually you get to pick numbers. I think that the
Well, there's
computer
quick
randomly
ones.
picks numbers.
Yeah, so
Yeah.
there's the random.
So the chances are that you're going to. So you're not. If you were picking numbers, you are. So. All right, guys. Time for dinner. I'll see you all Tuesday.
Thursday.
Thursday. Yes. I don't know.
Wait,